Right. Welcome back, everyone. Hope we had a good, productive weekend. We're going to just dive headfirst, per usual, back into where we left off. But for a second, I just want to remind you of the formulas that we gave you last time for the double angle formulas. We have sine of a double angle, cosine of a double angle, and tangent of a double angle. And I mentioned that usually these formulas are more used for algebraic simplifications in a calculus level math class. That's usually where these formulas come into play, but they can be used for more specific problems involving actual angles, but we usually have to set them up like in the problems we had here, not like in the previous section where we would have the sine of 15 degrees and we try to turn that into two different angles. Because usually, like if I say, well, do sine of 60 degrees by a double angle formula, you would go, well, why? I already know how to handle 60 degrees based on the right triangles you've given me. Let me just do it that simple way. And I'd be like, you're right, do it the simple way. But these formulas, we can actually kind of twist around and create what we call half angle formulas, which we'll ultimately do later, but we still have a couple more examples to do first. So, that was just a due date reminder, so we don't need that anymore. Draw, please, thank you. So 6.2 is due on the 28th. No surprise there. Example 1, we gave a triangle with two particular sides because the sine of it was 5/13, but we were in quadrant 2. If we were in quadrant 3 or 4, that would have been negative, by the way. And we found the sine, cosine, and tangent of the double angle. So we didn't actually know what the angle was, but by knowing this information about the angle, we were able to figure out anything involving twice the angle by the formulas above. And I said that you did have to memorize at least the sine and cosine on the left. I had said you need to memorize these two, although arbitrarily you could memorize one of these double angle versions of the cosine as well, because all three are interchangeable just by using Pythagorean identities. So you can memorize all three of them, or you could just memorize one and understand you can change between them by replacing a sine squared or a cosine squared with that Pythagorean identity. I had said the tangent one, I won't force you to memorize. Admittedly, most of the time we don't even use it because you can just do the sine and cosines, which are easier, and then divide them. Tangents in these sums and differences and half angles and double angles, the tangent's generally going to be the worst of the formulas, and maybe not the formula itself and memorizing it, but actually applying it, because having a tangent as a denominator tends to put other square roots or fractions in a denominator, and we've seen these complications. So there was our example 1, and we'll do another one like that in example 3, but let's do something a little different for example 2. Use a double angle formula to simplify, then evaluate. Now, for A, we're going to have 2 times the sine of 30 degrees times the cosine of 30 degrees. Admittedly, the instructions don't have to be done to find this answer. You know how to handle 30 degrees, so you could just say, oh, sine of 30. Triangle, it's, a half, or square root of 3 over 2. And then cosine of 30 is the other one of those. I'm not saying which specifically for reasons. Or you could recognize that this is 2 sine cosine. This is the right-hand side of that formula we did earlier. 2 sine cosine, where those two angles match. Now, if this was 30 degrees and the other was 60 degrees, the formula would not apply. But what we can do, just so we don't have to do 2 trig evaluations, is turn this into sine of twice that angle that's in there. Again, all I did was I just used that formula, but instead of going from the left side to the right side, I went from the right side to the left side. I recognize that I have 2 sine cosine where the angles match, so I can just say, oh, well, that's sine of twice the angle we see. Now, maybe that helps us, maybe it doesn't. Again, yes, you could have certainly done this evaluation straight out of the gate. It just means you're doing 2 trig evaluations. But here, this is now just the sine of 60 degrees, and it's only one trig evaluation. So it saves us some effort. That's what this can do for us in a more algebraic sense. Not just because, oh, we didn't know how to handle 30 degrees, so let's do this. Excuse me. This was just enabling us to only do one evaluation instead of two. So if sine of 60 degrees, you can, oh, I know that triangle. It's this one on the right, the 1, 2 square root of 3, the 1's opposite the 30, the 60 is opposite the square root of 3. So here's our angle. We're doing sine, so opposite over hypotenuse, and that's a square root of 3 over 2. So sine of 60 is square root of 3 over 2, and that is the answer. Sine of 30 degrees, if you wanted to do it the other way, just for, I'll discuss it, I won't write it. Sine of 30 degrees, so now we're here, would be opposite over adjacent, which is a half. And then you'd be doing cosine of 30 degrees, which is square root of 3 over 2. So you would have 2 times a half times square root of 3 over 2. You would lose a pair of 2's top and bottom because this one would cancel with one of them. But you'd still have the square root of 3 over the 2 from the cosine, and you would get the same answer. Well, Mr. Beckner, why bother showing us 30 methods to do one thing if that one thing was pretty simple and we could have done it after a couple of days in this course? Well, maybe these weren't 30 degrees. Maybe these were 15 degrees. And then you go, okay, well, the sine of 15 degrees I can write as the sine of 45 minus 15. And then you can use that formula from 6.2 and you'll have 4 evaluations to do. Then the cosine of 15 degrees, you would literally be doing the same thing and you'd have 4 more evaluations for a total of 8 evaluations, a lot more arithmetic, and it would be a pain in the butt. However, if you recognize, oh, well, this is the double sine formula, so I can just say that's the sine of 2 times 15, which would make that 30, and we know the sine of 30 would be a half based on that triangle. I would go from doing 8 evaluations to 1. That would be a more that would be a bigger strength of this problem if those had been an angle we didn't know how to handle originally. Now, if it had been 14 degrees, nothing's going to help us because we'd be going to 28. So it's a pretty rare situation that this is actually helpful, but you may find yourself in that situation repeatedly, so that formula would be helpful ultimately. Okay, but again, I don't want to leave the 15s up there. Just pause the YouTube video later if you want to see that as example C, maybe. All right, so next up, what if you had the cosine squared of 30 degrees, then minus the sine squared of 30 degrees? So once again, I could make both of these 15s. The formula would still end up applying, and you double the 15s to get 30s. And it would be necessary in that instance. But here, it's just an alternative. So someone goes, well, I don't want to do cosine of 30 degrees and sine of 30 degrees and then have to square them. Oof, that's just annoying, right? It's not that annoying, but it could be. So someone might go cosine squared minus sine squared. As long as these angles are the same, I remember because the Pythagorean's plus and the double angle formula is a minus, and the cosine's in front of the sine specifically. So you could go, oh, I remember this was that goofy cosine double formula. So you go cosine 2 times the angle you see of 30 degrees as long as they match. If that was 30 and 31, you couldn't do it. If it was 15 and 30, you couldn't do it. They have to match. Well, 2 times 30 is 60, so that's the cosine of 60 degrees. And you can go back to that triangle and prove that that is going to be a half. Yep. 60 degrees, adjacent is the 1, hypotenuse 2, and there's your half. Darn it, I keep minimizing too many things. So once again, I could have certainly just done cosine of 30 degrees, which would be square root of 3 over 2, and then square it to get 3 over 4. And then I could do the sine of 30 degrees, which is a half, and then square it, which is a fourth. And then you do 3/4 minus 1/4, which is 2/4, which is a half. It works, it's just more arithmetic. So again, some of you might be processing this type of stuff over and over and over, so you recognize efficiency and you do that. Or maybe you're just doing 2 homework problems and you don't recognize it, and then you end up taking the longer route. I mean, that's okay for now, but again, if you're going to be going through semester after semester of math, You have to learn efficiency. You have to remember things. There's a reason we teach them. All right. Example 3. So again, you could make a C and a D out of that by just changing all your 30s to 15s, which these end up being 30s instead of 60s, and then your answers would vary accordingly after your single evaluation. All right, example 3A. Not even going to put any words to start this problem. I'm just going to draw a right triangle. I'm not even going to put any pieces missing. Got some random angle here, theta, right triangle, and sides of 3, 4, those are our legs, and our hypotenuse is 5. I could have just given you the 3 and the 5, or the 4 and the 5, or whatever, and then asked you to find the third, but it's Pythagorean, we've done it before, let's get to the point. I'm just going to say, find the sine of 2 theta, assuming theta is in quadrant 1, I believe. Yes. Now, I did specifically say this is theta, which means that it has to be in quadrant 1. This isn't even an assumption, but I know some people will do reference triangles and forget their primes, so I try and be as specific as possible. So this is not a reference triangle, this is the actual triangle for the angle. All right, so sure, its sine is 4/5, but I want the sine of 2 theta. So the sine of 2 theta, we can use, we don't know, we can't just say, oh, we'll double it. That would be a terrible idea. The things in trig don't just double and triple in proportional ways. Trigonometry is very weird in that manner. So double angle formula from above would be 2 times the sine of the angle times the cosine of the angle. Now the last examples, we knew the angles, this time we don't. Doesn't matter. The sine of theta you just use based on the triangle, so this is the 2 up front. I'll do the sine part in blue. So the sine of theta would be the 4/5, so times 4/5. And then I'll do the cosine in red. That would be adjacent over hypotenuse, 3/5. Nothing to reduce, 2 times 4 is 12. Wait, I'm sorry, I did the 4 times 3 in my head. 2 times 4 is 8, 8 times 3 is 24. 5 times 5 is 25. So there's our answer. Easy as pie. I could ask you for the cosine of 2 theta, and then you could say it's cosine squared minus sine squared, or either of the other variations with the 1 and the minus and the 2 and only one of the sine squareds or cosine squareds. And it just depends which you think is easier. Me, I tend to prefer to only do one evaluation. So I would pick one of the formulas with just a sine squared or just a cosine squared. But there's nothing wrong with doing the cosine squared minus sine squared. B, another pretty common triangle with only whole numbers, the 5, 12, 13. Again, I could have asked for one of those missing sides via Pythagorean identities, but I put a prime there, which means it's a reference angle, and I'm going to ask for first we're going to say find cosine of 2 theta, assuming theta is in, I believe, quadrant 2. Yes. Quadrant 2. Now there are 3 formulas for this one. It doesn't matter which one you use. I'm going to go with the cosine squared minus sine squared. I find, even though that one's 2 evaluations instead of 1, I find more students memorize it easier because it's so close to Pythagorean. It just does a minus instead of a plus, and it swaps the order. Then you don't have to remember which one the 2 goes with. It just becomes a little more of a hassle. Again, I think I've even admitted that most variations of formulas I don't memorize. I just do that simplification in my head or on paper to get it. So I go, oh, is it 1 minus the 2 sine squared, or is it 2 sine squared minus 1? Because one of them has the trig term first, one of them has it second. It's tough to keep that organized. So just pick one of the 3 to memorize in general, and then understand how to rearrange them, or if you have to, memorize all 3. Because I can tell you in calculus, if you don't know how to go from one and find the other 2, you will have to memorize all 3 at some point. unless you get one of those rare calculus teachers that lets you use formulas for everything. And if you have me for calculus, that ain't me. So I'm going to do the one that I think is easier to remember, the cosine squared minus sine squared. So I'll even write out that formula just to start things. So cosine squared minus sine squared. So you're going to do the cosines and the sines and then square the results. So the cosine of this theta prime would be adjacent over the hypotenuse, which would be 5/13 just looking at the triangle, but that's wrong. Why is that wrong? Because we're in quadrant 2. We are in quadrant 2. That is a critical component to remember, because cosine and tangent are negative in quadrant 2. So when I do this cosine, I got to give it a minus. Now, I will admit, you can actually do that wrong because of the squaring, and you'll still get it right. Squaring the negative makes a positive. So that's one of the nice features about this problem. You can actually get the answer right, even if you goof up that detail. And, you know, I don't like that you can get it right even with goofing it, but it's just convenient. And then minus, this minus sign's there. And then the sine squared. Now, sine's positive in quadrant 2, so no extra negative there. And then the sine would be 12/13, but because of the square, you still do need the parentheses. It wasn't just because of that negative we needed the parentheses. The squaring said we also needed it. And then your square tops and bottoms. -5 squared is +25. Then over 13 squared is 169. Then your minus symbol. 12 squared is 144. Over 13 squared is 169. 25 minus 144, I believe, is 119. Yes. Over 169, but the larger was negative, so the answer should be negative. So there we are. Now again, I could have asked for sine of 2 theta and you do 2 sine cosine. I could have then asked for tangent and then you just divide those two answers to make it easiest to process. But I didn't. Just focused on one each. So we were doing a cosine. The answer was negative. That says, just for extra, you know, I'm not going to say credit, but extra knowledge, since this is negative and it's a cosine, cosine's negative in quadrant 2 or 3. Now, if the original angle was in quadrant 2 and we're doubling it, I find it highly unlikely that the doubled angle is going to be in quadrant 2, so it's probably in quadrant 3. But you cannot definitively say that necessarily. I mean, you can, but I'm not going to get into all that. You went from being between 90 and 180. If you double that, that says the answer to the double angle has to be between 180 and 360. Since it's negative, you know it's in quadrant 3 and not quadrant 4. You know it's not quadrant 2 because doubling the original parameters says you can't even be in quadrant 2. I mean, even just thinking it logistically, if your original angle is, say, 120 degrees, you double that and you get 240. If the smallest angle it could have been is 91, you double that, you get 182, which is quadrant 3. There's no way a doubled angle is ever going to be in the same quadrant, traditionally speaking. Now, notice I said traditionally. If you're talking about something like the cosine of 500 degrees or the sine of 2010 degrees, that would be another story. I'm just talking about going originally from 0 to 360, using standard angles, not coterminal angles past 360. Alrighty, so that will finish us up with the double angles. Now let's move on to the half angle formulas. And the half angle formulas are honestly just rearrangement of the double angle formulas, but not the ones on the left side of the page. It's these two over here. So what we're going to do is we're going to take these two formulas, but now we're going to change this theta here to a theta over 2, which makes this 2 theta just a regular old theta. So again, this becomes theta over 2. I'm just giving you the rundown of what we're about to do. So we're going from theta and 2 theta to half and whole. And we're going to solve for the sine or cosine. So for this one, we're going to solve it for sine, which means we'll have to undo the squaring part. And then this one, we're going to solve for the, oops, did that just slightly wrong, for the cosine. Here we go. That looked a little goofy too, because I started taking it too far. There we go. We're going to solve each of those for sine or cosine, and that's going to give us our half angle formulas. So we're going to prove them, and then we're going to write the formulas down. All right, so proof of half angle formulas. Again, just kind of formally typing this up. We will start with the double cosine formula variations. My typing and what's showing on screen is at a different pace, which is why I keep making these errors. Start with the double cosine formula variations. Solve for either sine or cosine, whichever is present. So for the first one we'll do, we're going to take cosine, oh, and also and you're going to half each of the thetas seen. So the 2 theta turns into theta, the theta turns into theta over 2. Just to make it a little more sensible with half angle, so you'll see halves in there somewhere. All right, so what originally said was cosine of 2 theta, now I just write cosine of theta, that equals 2 cosine squared. Instead of writing theta, I write theta over 2, and then the minus 1. So we're going to add 1 to both sides, which will give us the cosine of theta plus 1 equals 2 cosine squared of theta over 2. Then we're going to divide both sides by 2, just basic algebra, even though the trig makes it look ugly. So that's cosine of theta plus 1 all over 2 equals cosine squared of that half angle. And then whenever you have something squared equal to something else, you just take a square root of both sides, right? Question mark, question mark, question mark, no. You take the plus or minus square root of both sides. That was a property. If you had me for pre-calc 1, you heard me say 500 times. Probably don't forget that plus or minus when you take square roots. So what we end up getting is plus or minus, big old square root, cosine of theta plus 1 all over 2 is equal to cosine of that half angle. That is the, I'll end up swapping the left and the right sides, but that's your half angle formula for cosine. Similarly, if we take the, I'm just switching colors for visual reasons, sine of theta equals, and so this was originally sine of 2 theta. I'm sorry, not sine. What am I doing? Cosine. I'm putting the sine in the wrong spot. This was originally cosine of theta, cosine of 2 theta, so now it's cosine of theta, equals, now this one was 1 minus 2 sine squared theta originally, but I halved all my angles, so that's now theta over 2. You're going to subtract 1. You don't actually put the minus 1 inside the cosine, though, to give us cosine of theta minus 1 equals negative 2 sine squared theta over 2. You're then going to divide both sides by negative 2. So that's now going to be a negative cosine plus 1 all over positive 2. We don't like negatives being left in the bottom, so I just changed the signs at the top, equals the sine squared of that half angle. Then you take your plus or minus square root of both sides. Plus or minus only goes on the side of the thing you're not solving for. Hold on, give me about 5 seconds. Okay, and then that's plus or minus square root negative cosine theta plus 1 all over 2. I was not supposed to be doing that in red. I hit blue and it didn't register. Plus minus, actually I might have hit red, now that I think about it, equals sine of half of theta. So these are your formulas, but what I'm going to do is, because this is a minus cosine and this is a positive cosine, but the ones are both positive, I'm just going to swap the order of the ones and cosines inside of the radical, and I'm going to swap the left and the right sides entirely. So our half angle formulas. Now, if you just took those two things and divided them, you'd get the tangent formula. I'm going to skip showing the work on that. I'm going to leave that as an exercise to you. So just putting these in a more appropriate format. Sine of theta over 2 equals to plus or minus square root, so that's the one we just got, 1 minus cosine of the regular angle, and then all over 2. And then we have the cosine of a half angle equals plus or minus big old square root 1 plus cosine of theta all over 2. And if you do sine over cosine, you're going to have a square root divided by square root. The 2's and the bottoms are just going to cancel, and you'll end up with 1 minus over 1 plus. It's extremely easy to show as long as you know how to do your fractions divided by fractions, which we have practiced several times. So plus or minus square root 1 minus cosine theta over 1 plus cosine theta. Now, remember how there were 3 versions of the double cosine formula? There's also 3 versions for the half tangent formula. Not going to show the proofs, but I will say that while this is the easy one to prove, the next 2 I'm going to write are the easier to apply, and the reason is because you have a cosine in the bottom of a square root. So this thing right here could be like square root of 3 over 2, so you got a fraction inside of a fraction. You got square roots and denominators, and then you got square roots and denominators of something that's got a square root of a fraction. This is just a nightmare of algebraic simplifications and arithmetic simplifications. So this is not always the easiest one to use. So also, tangent of a half angle is equal to 1 minus cosine of theta. Great. All over, not 2, I'm looking at a 2, over sine of theta. My formulas, but when I look at something, it just makes me write it. Or it could be sine of theta over 1 plus cosine theta. So there are 1, 2, 3 versions of this formula. These are the easier ones on the bottom. These 2 versions are much easier because there's no big square root. So if this cosine might have a square root in it, yes, you'll still have to simplify compound fractions and rationalize denominators. But having that other square root just makes it nightmare fuel. So I'm not giving you the proof of this thing being the same as this thing being the same as this thing. But what's interesting is like they have these 2 right here have a lot of same components, a cosine and a sine. The sines in the top only or the bottom only, and the 1 plus or 1 minus has a cosine in the top only or bottom only. Now, remembering which one goes where might be a struggle, but if you memorize one, the other is just flipping it and changing a plus or a minus. In fact, if you take, I'll tell you how you can do it. You can take the second one and maybe you multiply top and bottom by a conjugate and maybe some Pythagorean stuff. Maybe that would get you to this one. But what is fun is if you go back a few sections, back to when we were working with trigonometric identities, the proofs making the left side match the right side, where we kept saying QED. This right here is a lot of trig teachers and trig textbooks' favorite ones to give students to prove that those are the same thing. And there are a lot of different ways you can prove it. You can cross multiply, you can do conjugates, everything's already in sines and cosines. You could move everything to one side and get an LCD. You could just multiply both sides by the LCD. I'm not even going to go through all of those. So the half angle formulas, I find these, if you need to do an angle evaluation, much more helpful than the double angle formulas. Again, double angle formulas are usually just helpful for trying to turn a bunch of different things into less things, or to be in calculus and turn something that you don't have a formula for into something that you do have a formula for. The reason double angle formulas aren't that helpful for is like, okay, you've got 60 degrees. Well, that's doubling 30, which you already knew how to handle. Or maybe 120 degrees. Well, that's doubling 60, which you already knew how to handle. Or 150 degrees. Well, that's doubling 75, which you don't know how to handle. So that doesn't even help. There's not a lot of instances where doubling an angle gives you one that you know how to handle where you didn't know how to handle it originally. But there's a lot of times where you've got an angle that's half of what you would know how to handle, like 15 degrees. So 15 degrees, so far we worked with that by doing a difference of 45 and 30. But now you could also say, hey, 15 is half of 30, so let me use a half angle formula. And in that half angle formula, you'd be evaluating with 30, which you know how to use. So that's the strength of half angle formulas. And I just have one final memo. I'll keep it in blue since all these were blue. And that is that you see these pluses or minuses because when we took a square root, we had to do a plus or minus. But with trig, it's not possible that a sine of an angle is both positive and negative. This is actually one of those, it's an either or scenario, it cannot be both. So you pick the plus or minus based on the quadrant of the original angle. For instance, if I gave you a problem using 15 degrees, 15 degrees is in quadrant 1, everything's positive in quadrant 1, so you'd pick the plus. If I gave you something involving, say, 112.5 degrees, spoilers, you would say, well, that's in quadrant 2, so I'd pick my plus or minus based on whether I was doing a sine or a cosine and whether it's positive or negative in quadrant 2. Sine positive, cosine negative. All right. Now, I will give you these formulas on a formula sheet. I will not ask you to memorize the half angle formulas. I will give these to you. So far, I've been pretty clear with what I'm going to give you, and I'm actually going to make my screen go blank for a minute. And hold on, how do I do that again? Nope. There's supposed to be a pause share button. And something's changed. I'm thinking. All right, I think if I do that, that's all you'll see. It doesn't really matter otherwise. Nope, not that. Open the wrong thing. Bear with me. All right, there we go. New share. I'm kind of curious if, so you should now see a formula sheet. Could you see that 15 seconds ago? If anyone in the chat just wants to answer that, I'm curious if that actually worked. If it didn't matter. I'm just curious. So this is what your formula sheet is going to look like for test 2. So these are the formulas that you'll have or not have for the test. So you'll notice that the sum and difference formulas for sine and cosine are all blank, as I promised. You will notice that the tangent sum and difference formula, I gave you all the tangents in ones, but I did not give the pluses or minuses on them. For the double angle formulas, I actually do you one better. I don't give you sine, but I am going to give you all 3 versions of the cosine. You know what? I might change that. I don't like that. I used to give this one, but I've already said that I've asked you to memorize it, so I kind of want to keep my word. Whatever, I will give this to you before the test. You will all receive an emailed copy of this, and then you'll know whether you have this one or not. But if I give you these 2, you could find the other one by doing some replacements, right? So this one's questionable. I know it says I'm giving it to you right now, but I'd originally said I wasn't going to, so I'm probably going to hold my word, so expect that to go away. But I give you the tangent. I give you all the different half angles for sine, cosine, and tangent. So this is your formula sheet. Again, maybe this will be scratched out. Maybe, probably. Okay. So now that you know what your formula sheet will look like, let's try out an example using this, knowing that you will not have to memorize your half angles. And we're up to example 4. And I'm going to explicitly say use your half angle formulas to find, because one of them, at least one of them, there is an alternative way. The first one we'll do is cosine of 112.5 degrees. Now again, if that was in radians, you'd probably want to convert it to degrees, because you're not going to know what that is in radians off the top of your head. 112.5. Okay, first of all, the fact that this is a 0.5 is a giant clue that a half angle formula is going to help you. Now, when we say half angle, we're not saying to half the angle that you are looking at. We're saying that this is half of an angle you should try to get. This is half the goal angle. So you got to think, well, what is twice 112.5? Well, that would be 225 degrees. So 225 degrees, actually, let me not write the equals yet. That's the doubled angle. This is the half angle. This is the doubled angle. The doubled angled, the double angle. So since we're going to use a half angle formula, again, this is half of an angle we know how to use, and we know how to use 225. You might say, Mr. Beckner, that's not the 30, 60, 90, or 45, 45, 90. No, it's not, but there's a reference angle that references those 2 triangles, one of them. So we're going to say use a half angle formula. And for the cosine, we said it's plus or minus, and it's literally plus or minus, not both. Big old square root, 1 plus cosine of the doubled value, which is 225 degrees, all over 2. And then you've got to ask, which one do we choose? Do we choose the plus or do we choose the minus? And that's based on the original quadrant. Not the original quadrant of 225. 225 is not the angle we were asked about. We're talking about 112.5. So 112.5 is in quadrant 2. So, and we're doing a cosine, we choose the negative. So it's negative specifically, square root of 1 plus the cosine of 225 degrees all over 2 inside the radical. Going down here, well, cosine of 225 degrees, you could use a reference triangle if you need to build that up. I think I can probably squeeze it here. So 225 would be this whole angle. That's your 225 degrees. So the reference angle we need to build would be right here. This would be the theta prime, which theta prime will be 225 minus 180. which is 45 degrees. If you try and do 180 minus 225, you get negative 45, and it says you did it backwards. But this angle is in quadrant 3, and we're doing a cosine of that, so it should be negative. That is a lot to have to keep up. So this is in quadrant 3, so we just choose the negative. The cosine, that looks like SOS, doesn't it? The cosine of 225 degrees should be the negative of the cosine of 45 degrees. Now I'm going to come back to the original formula. So this is equal to negative square root 1. Now plus cosine of 225 will now be a 1 minus cosine of 45 degrees, then all over 2. Cosine of 45 is the 1 square root of 2 triangle, which is right here. Cosine would be 1 over square root of 2. But we should know by now that we don't want to write that as 1 over square root of 2. We want to write that as square root of 2 over 2. Rationalize that denominator. And then that's all over 2. So again, this cosine of 45 was 1 over square root of 2, which when you multiply top and bottom by square root of 2, you get that. Excuse me. Uh-oh. You got numbers in the bottom of a square root. You got fractions inside of fractions. So you got lots of things to clean up here. The easiest thing to do, the easiest way to process this would be to identify the LCD of all the small fractions. The only small fraction you have is that, so its LCD has to be 2. And that's what you'll multiply all the tops in the inside by. So this becomes big negative, big square root, and then it's 2 times the 1, and 2 times the square root of 2 over 2, and 2 times the 2 in the bottom. Okay, so this is negative, big square root. The bottom is very obviously 4. 2 times 2 is 4. The top left, 2 times 1 is 2. And then minus this 2 in the top will cancel with that 2 in the bottom, which was the entire reason we did what we just did. So with those 2's gone, that's now just a minus square root of 2. All right, well, we have a square root of 4 in the bottom. We're not allowed to have square roots of denominators with answers, or square roots in denominators of answers. But we do know we can split this up. And if you don't, here's your friendly reminder that a square root of a fraction is a fraction of square roots, and the square root of 4 in the bottom is just a 2. The top is extremely complicated for us. We do not know how to simplify that, so leave it alone. Square root inside of a square root, that is a brain buster. So that's your answer. So that's the first instance. You may have even seen square roots inside of square roots in a math class. It's possible you've seen them before. When we talk about like infinite sequences and series, you'll get square roots inside of square roots for approximating some really cool numbers. But I don't want to get into that. That would waste a lot of our time right now when we are, not exactly ahead of schedule. But just know that this is okay to have square roots inside of square roots. You can't have square roots in bottoms. You can't have square roots of fractions. But you can have square roots in square roots with us for now at least. And when I say for now, it really doesn't go away. You start seeing it a little bit more and more here and there. All right, sine of 15 degrees. And I want to point out the reason I gave the instructions of use the half angle formulas, because this one, you could say, oh, well, that's the sine of 45 minus 30, and then go sine of 45 times cosine of 30 minus cosine of 45 times sine of 30. And we may have even done that exact problem before. And you could then compare that answer to the one we're about to get, because spoilers, they're not the same answer. They look completely different, but you can mathematically prove that they're the same with methods and techniques that all of us should have in our tool belt. In fact, I have made that a test question or bonus question before to prove that the answer using half-angle formulas is the same as the answer using not double, sum, or difference formulas. So again, yes, you could say this is 45 minus 30, but I want to practice the half-angle stuff. So you say, well, I don't know a right triangle with 15 degrees, but I know that 15 is half of 30, and I do know how to handle 30. So let's use the sine formula, which was plus or minus. Again, 15 is half of 30. I'm not going to write it down this time. So we're going to go big old square root. And the sine formula, instead of 1 plus, it's 1 minus. That's the only difference. But it's still a cosine in here. And it's not 15 degrees, it's 30 degrees. What we have is half of what we know how to use. That's why we call it a half-angle formula. And then that's all over R2. Every semester, I always reconsider giving these formulas to my students, the sine and the cosine ones, because they're so close to each other. And you might actually be the last class I give that formula to. All right, so before we move on, 15 degrees was in quadrant 1, so we pick the plus out of this plus or minus. Again, it's not based on the 30. Now, when I do this evaluation, I may have to think about what angle what quadrant that's in as well, like last time. But it's not picking the plus or minus based on the 30. We pick the plus or minus based on the original angle. So I'm going to write the plus just for emphasis. So square root 1 minus cosine of 30 degrees all over 2. Cosine of 30 degrees, we're just using one of those triangles we already know. We don't need a reference angle or anything like that. So 30 degrees is here. Cosine would be square root of 3 over 2. So that's the positive, which I'm not going to write anymore. 1 minus square root of 3 all over 2. Square root of 3 over 2 all over 2. I read that slightly incorrect. And you got a square root inside of another square root, but we know that's not an issue. We still have a number inside the bottom of a square root. That's a problem. We got many fractions inside of big fractions. That's a problem. This is like the 10th time these issues have come up. So this will be like the 10th time I remind you, you got to know how to handle this particular layer of algebra. So to get rid of the individual denominators, we find an LCD, which is the only individual denominator, and that's the 2. And then we multiply all the tops by that. So big old square root, and then the 2 times the 1 minus the 2 times the square root of 3 over 2, and all over the 2 times the 2. I'm putting those in red. Boom. Why do we do that? So those 2's cancel. There's always logic and reasoning to the things we do. So the square root of 2 minus square root of 3 all over 4. You can split the square roots if you like. So that's the square root of 2 minus square root of 3 all over square root of 4. Square root of 4 is 2 in the bottom. Top, we got no clue how to handle that. Square root got just a little too long. There we go. Good enough. That's all we can do. You might think, oh, well, maybe some conjugate idea would work. Maybe. Well, let me just square top and bottom. Can't do that because it's not an equation. The technique to simplify this to not have a square root inside of a square root is actually pretty insane. It uses stuff we've done, but it really feels like there's no rhyme or reason to any of the middle steps. But again, thankfully, my math lab takes these answers just like any program should for a normal trig student. You know, if this was like Harvard level trigonometry, another story. So I want to pull up something. I always forget if I do sine or cosine previously. I don't know what I just clicked. Can't tell, this isn't my computer. Did we do sine of 15 degrees? We did cosine. So close, but. So if we just did the cosine of 15 degrees with a half angle formula, you would be able to compare it to this. And the sine answer is pretty similar with the square roots, 2 of them in the top, there's 4 in the bottom. You know, it might be different numbers, it may be only be 1 square root. But again, very different looking answer, that if I had asked you for the sine of 15 degrees here, which I already told you how to do it, it would be sine of 45 cosine of 30 minus cosine of 45 sine of 30. Do all that stuff and you'll get an answer that looks similar but different. You could then set those two things equal to each other. This answer, which you don't actually see, I just talked through, set it equal to this answer, and there's some math you could do to make them prove that they are the same value. Alternatively, you could just stuff them in a calculator to show the decimal values are the same, but it's not really a proof now. That would not earn you bonus points on a test if I did that, which I'm not doing bonus points on tests in this format of a course online. Because there's so many other opportunities everywhere else to do things. C, last one of these, tangent of 22.5 degrees. Again, with a decimal of 0.5, that's a giant clue. Half angle is the way to go. You don't want to do sums and differences because in the sum and difference, you'd need halves in both of those, or at least one of those, and that's not going to really get you anywhere. You're always trying to turn this into an angle you know how to handle, or multiple angles you know how to handle. All right, so this 22.5, this is half of, if you double that, you get 45. 2 times 22.5 is 45. So this is half of 45 degrees. And we know how to handle 45 degrees. We don't know how to handle 22.5, so we should use the tangent half angle formula, which I'm going to do this in blue because I'm not actually going to use it. The original formula I gave you was plus or minus big old square root, and it goes 1 minus the cosine of the doubled angle, 45 degrees, over 1 plus the doubled angle cosigned. And you'd say, all right, well, what do we pick, the plus or the minus? Well, this is in quadrant 1, the 22.5, so we pick the plus. So we go plus big old square root 1 minus cosine of 45 degrees, 1 plus cosine of 45 degrees. Cosine of 45 square root of 2 over 2, so you'll have 2's in the bottoms to clear, and it just gets a little messy. It's not terrible. It's the same thing as what we already were talking about, except for the fact that after you clean that up, you'll still have a square root in the bottom, so then you'll have to multiply top and bottom by a conjugate inside the radical. Ugh, it's just more work. So we said earlier there's actually 3 versions of the tangent. These are easier to manipulate, even though this formula flows naturally from a derivation because it's literally just this thing divided by this thing. The 2 in the bottoms would cancel. The square roots just say put everything under a square root, and the plus or minus just have the plus or minus. What's awesome about these 2 formulas, it's no big square root. There is no plus or minus, which means you don't have to do any kind of sine SIGN prediction. It's just now you have 2 trig evaluations instead of 1. I think that's easier. Now, which one should you pick? The 1 minus cosine in the top or the 1 plus cosine in the bottom? Me personally, I usually prefer this one. That's my favorite because then the bottom will not have a 1 plus, which means if there's square roots and bottoms here to fill out, you wouldn't have to rationalize the denominator in the goofier way. It's just multiply top and bottom by the square root. So this is my winner chicken dinner, 1 minus cosine over sine. So in difference, I'm going to go tangent of 22.5 degrees equals no plus or minus, no square root. It's just the sine in the top, I'm sorry, the sine in the bottom. Blah. And that this shouldn't be theta, it should be doubled the half angle, so sine of 45 degrees. And if I made you memorize it, you just have to remember, is it plus or minus here? Well, it turns out it's minus, but again, I'm not making you memorize it. You may be the last class to get that benefit. Cosine and sine of 45 degrees are both square root of 2 over 2. So it's 1 minus square root of 2 over 2 all over 1, I'm sorry, not 1 plus, just square root of 2 over 2. And that's because the opposite and the adjacent are both 1, the hypotenuse is 2. So you get 1, I'm sorry, 1 is square root of 2, so 1 over square root of 2 becomes square root of 2 over 2. Then you do your LCD business. Your LCD of the individual denominators are 2 and 2, so it is 2. So we say equal take that 2 times the 1 times the 2 square root of 2, and then times the 2 square root of 2 over 2 in the bottom. So these 2's will cancel. These 2's will cancel. Giving us just 2 minus square root of 2 over square root of 2. All right. Well, Mr. Beckner, you said in that other problem you were going to have square roots in the bottoms and you're still going to have to rationalize the denominator. Again, you would have had to do that conjugate style, whereas this one, you're just going to multiply top and bottom by square root of 2, since the bottom is just a monomial. If it was a binomial, if this was a 1 plus or 1 minus square root of 2, it means you're multiplying top and bottom by its conjugate. So this is just a little easier. So we get 2 square root of 2 minus square root of 4 all over square root of 4. Again, this square root of 2 times square root of 2 and this square root of 2 times square root of 2 gave us the square root of 4's, which are both 2's. So 2 square root of 2 minus 2 over 2. And what's really cool is all of these have a common factor of 2 on the outside. So 2, 2, 2, those are all now 1, 1, and 1. You don't need a 1 in the denominator by itself. So it's just square root of 2 minus 1. It actually is the simplest answer of all three. Who would have thunk that the tangent answer would be the simplest looking? I wouldn't at first glance. And if you had done it the other way, you might not have actually figured out that it's this simple. You may get something that is algebraically the same, but much uglier in appearance. So half-angle formulas are really useful for evaluating trig functions of angles that you don't know how to handle them, but if you were to double it, you would know how to handle it. Double angle formulas have that same feature. It's still a doubling, but usually you don't have an issue handling the first value anyways. Doubling it is generally not going to help you. If you know how to handle the first one, you definitely know how to handle the second one. If you don't know how to handle the first one, it just works a little differently. So again, I've already mentioned that the double angle formulas, this is really scrolling slow for some reason, these are more useful for algebraic simplifications like proofs and equations and calculus stuff. If I ask you for the sine of 120 degrees, you don't want to be thinking in terms of 240 degrees. I'm sorry, if I asked you for 240 degrees, you wouldn't want to think in terms of 120 degrees because it doesn't help you. You still know how to handle both of them, so there wouldn't be any point to that. I did not mean to leave all of that there. Oops. Ah, shoot. That was weird. Just erasing some things. And it's erasing too much at a time. That's all right. Again, the double angle formulas, if going from left to right, is all about halving it. But the half angle formula is all about doubling it. So again, when you think you need to use a half angle formula, what you're looking at is half of what would be useful. The double angle formula means that you're looking at what you feel like would be twice of what's useful. Now, you might say, well, Mr. Beckner, this problem, that's not the way you did it. And that's because these were the right-hand sides of the formulas. And this is a very unusual thing to see, that this just happens to be algebraically simpler. This is much more of a cookie-cutter math problem that teachers use just to make sure a student knows the formula inside and out. There's really not a lot of cases in math where you would want to apply that. Notice I said not a lot, there's always some. All right, so that is 6.3. Now, I'm looking for something. Did I not have it in here? I'm not seeing it. All right, so I'm just going to take a minute. Pause for a second. Going into Canvas to show you something. It's not in here. All right, that's fine. I'm not sure where this file is that I've got, but there's a file I'm going to give you that is the notes from the fourth section that I already mentioned. We're not going to go over officially. It's kind of funny. I can't even find a piece of paper in my notes right now because I usually have it buried since we don't cover it. But I still want you to see all the formulas and stuff because you never know when you might come across it in a later class. So here's what we'll do instead. Pull up the textbook since my piece of paper is hiding from me. Oh, come on. Patience is a virtue, isn't it? All right. How far are we in there? Chapter 2. Chapter 5. 6.3, that was close. 702. All right, 6.4, product to sum to product formulas. This is not part of our curriculum. You will not be quizzed or tested or homeworked on this, but I just want to show you the formulas. I'm going to put them on the screen just for a minute. I'm not going to go over any proofs or how they came about, but this is something that, once again, can be useful in calculus here and there. Admittedly, there's not a lot of times where you would want to do this in a trig class outside of just a cookie cutter problem that says do this. But if you have a sine of one angle times a sine of another angle, you can turn this into 1/2 times all of this stuff where you add or subtract these angles. The way these are derived just uses the sum and difference formulas, and it combines two of them by adding them or by subtracting them and solving for one thing or another. So like, remember how the cosine formula had cosine, cosine, sine, sine? So if you took that formula and the two variations of it, the plus version and the minus version, if you added those together like a system of equations and solve for sine, sine, you would get this. Similarly, if you solve for cosine, cosine, you would get this. So it's just saying that sometimes you'll have maybe a sine of 15 degrees and a sine of 45 degrees, and you don't know how to handle at least one of those two things, but you could say, oh, okay, well, that's cosine of 45 minus 15, which is 30, and then a cosine of 15 plus 45, which is 60, and then both of those happen to be convenient angles. So maybe you have something that you only know how to handle one of them, or the other would just be a pain in the butt. Like I said, 15 degrees, you could do half angles, or some indifference inside of that. So again, it's just about convenience. And then that's the product to sum. The other way is the sum to products. And they look like this. So if you have a sine of 15 plus sine of 45, you can turn it into this thing where you'd be adding the 15s and 45s or subtracting them to get your 60s and 30s. So again, the 45 wasn't an issue. It was the 15 that you'd go, well, that would be annoying to have to deal with via the sum and difference or half angle formulas when this one's already clean. but I recognize since it's 15 and 45, I can add them and subtract them and get two nice angles. So then you apply this formula. Again, it's all about convenience, but this is not anything I'm going to test you on. I'm just going to, again, I'll load up a file at some point this week. I'm not even going to promise to do it today because I'm immediately running out the door as soon as this class ends for something. But again, you just never know when you might need these formulas in a calculus course, in an advanced differential equations course, in a really weird statistics course. I don't know. All right. Again, not on any kind of homework, not on any kind of test, just showing you things that might be relative to your math life later. So with that being said, let's start out 6.5. Trig equations. So lots of space. The ultimate point of this chapter. Me giving you an equation like tangent of x minus 1 equals 0 and asking you to solve for x. Or 3 sine of x plus 17 equals 5 cosine of x minus 45 and asking you to solve for x. This is where everything really comes together. So a couple reminders. Sine, cosine, cosecant, and secant all have period 2 pi. Whereas tangent and cotangent have a period of pi. Why is this an issue again? Because you might have a problem that says solve. You might have a problem that says solve on 0 to 2 pi or 0 to pi or whatever. You can have more than one answer to equations, as we've already seen. We saw this in chapter 5. I would give you a problem like the cosine of theta equals a half, find all theta, and there were 2 answers. Well, I usually said I would say find cosine of theta equals a half, find theta where we're just saying from 0 to 2 pi. But quite often we're going to not give any restrictions on this. So if you just said the answers are, I don't know, pi over 6 and 7 pi over 6, I'm not saying those are correct, I'm just spitting out 2 answers. If I don't put any restrictions on the domain, you're not even close to all of the possible answers. Because every time you add 360 degrees, that answer works again, and it works from both roots. So there will be infinite answers if you have no restrictions on the domain, and you'll have to use an additive value to symbolize that. So if your solutions have a domain that isn't restricted, let's consider periodic nature of these functions. Sine, cosine, cosecant, and secant, you just add, and I want to write this using my pen, 2 in pi, where n is an integer. Integer meaning it can be 0, 1, 2, 3, 4, 5, 6, 7, or -1, -2, -3, -4, -5, et cetera, et cetera. So this is just us adding or subtracting 360 degrees over and over and over. That's all that says. I fit it all here. For tangent or cotangent, because their period is pi, you're simply going to add n pi, which is just adding multiples of 180 degrees, where n is still an integer. In integer. So I'm going to treat this much like much like the verifying identity section, where I'm going to give you a whole bunch of techniques at first. And in fact, with only 3 minutes left, we're not going to get very far into this, but the first technique is, if there's only one single trig term, or one type of trig term, isolate it. Get it by itself. That's what that means. So that's one technique. So if you only see signs littered everywhere, just move all the signs to one side, move everything that doesn't have a sign to the other side. If the inside of the function is not just x, you'll need to do n equals 0, 1, 2, 3, etc. until your answer goes past one period. We'll explain why that is next time. It also won't be something we get to immediately. And we're going to go ahead and pause there. So we'll come back, we'll read this off, we'll continue writing, and we'll start some examples. This is very likely, highly likely to not be finished next class. So as much as I'd love to finish that section on the 28th, I really do not anticipate that. Because I'm looking at 1, 2, 3, 4, 5, hold on, 6, 7, 8, 9, 10 examples. So that's probably 2 full classes. So if you're looking for an idea for the test date, I am anticipating that we finish this section on November 2nd, which means the test would be November 9th and 10th. So again, test 2 will likely be, not guaranteed yet, but November 9th through 10th. Question mark, probably, not saying until we finish the material though. So on that note, have a good one. We'll pick up where we left off next class. We did finish 6-3, so that homework is due in 1 week. Besides that, take it easy, everybody. Email me if you have any questions.